Welcome to part 5 of the lecture on catalytic organometallics. In the preceding lesson, we already had this example of an intramolecular Heck reaction. So we had a palladium 0 catalyst about, generally about 1 to 10%, and of course solvent, and you need a base because essentially you eliminate HBr. So the mechanism of this reaction is, first of all, the palladium 0 makes an insertion reaction into the carbon-bromide bond. It is an oxidative addition reaction because palladium changes the oxidation state from 0 to +2. Then a carbopalladation occurs to this CC double bond, clearly a syn-selective process. After that syn-carbopalladation, we have the following situation. Forming a 6-membered ring here in the middle. Syn-carbopalladation means that the aryl group and the palladium are on the same ring, on the same side of that cyclohexane ring, and preferentially also this substituent is on the same side, all substituents on the same side. Well, and the final step then should be a beta hydride elimination. This is also a syn process. The hydride in this position, the hydrogen in this position, has a trans position. Here we have also a syn hydrogen, therefore the elimination occurs to this position, and therefore this should be the final result. Yes, it's the same. 74% yield. And we don't have the double bond in conjugation to that aromatic ring. Next, we should have a look at some further examples, but as exercises. A spirocyclic system. You should try to figure out what is an appropriate starting material for synthesizing this by an intramolecular Heck reaction. So this is a retrosynthesis arrow. This is the synthesis arrow. Further examples. Here again, synthesis. What will be the result of the palladium catalyzed process? And even more examples to follow. Again, palladium 0 catalysis, and always the presence of a base. And similar reaction conditions also for the last case. So, please figure out solutions for the problems. 3 times what is the product of the palladium catalyzed process, and in one case, what is the appropriate starting material to synthesize this structure. Meanwhile, I have modified this drawing of the intermediary palladium-2 complex. The structure that was depicted before was not wrong, but looked a bit strange. This looks better now, of course. So, let's go through the problems. What is the starting material, an appropriate starting material for this structure to achieve a synthesis of such a structure? Well, Heck type reaction, an aryl or vinyl halide reacts. That means we are forming a CC bond starting from an sp2 hybridized center. This one would be suited, and this bond should be formed, therefore. Okay, that means we should have a functional group here, usually a halide. Best is iodide or bromides, works best, but chlorides can also undergo a Heck type reaction. So, and we have to connect this carbon with that one, with the alpha carbon at the carbonyl group, and therefore here the double bond has to be located. Well, we have a selectivity problem then. We could imagine the CC bond formation from this position to that one, giving rise finally to this product. This is then, of course, to be classified as a 5-exotric cyclization according to Baldwin. And indeed, those are normally preferred to 6-endo trick. One could imagine also the CC bond formation from this position to that. However, the other one, the 5-exo trick, is preferred. You have certainly noticed that in this case a chiral center is formed, and indeed with BINAP, an atrope chiral ligand, bidentate phosphine ligand with this structure. So a binaphthyl moiety with 2 diphenylphosphenyl substituents and a chiral axis. Here, with this ligand, we can achieve an 89% yield and a 90% enantiomeric excess has been confirmed. Next example, what will be the result of this Heck reaction? So, carbopalladation will, after oxidative addition of palladium 0 as usual, then the carbopalladation will connect this carbon with that one, forming a 6-membered ring. On the first glimpse it looks a bit strange from here to there. Well, but nevertheless, let's draw that. So, the palladium iodide would be located at this position, and a Syn elimination would then occur here. This will be the result. First glimpse, a strange drawing. However, it is correct. Well, if you would draw that similar to what you are used when you are drawing Norbonane moieties, but now with more ring positions. Then this kind of drawing would result, and well, okay, maybe looks better, maybe not. Yeah, it's your choice. 88% yield was obtained in this case. Again, also this reaction you could perform potentially under enantioselective catalysis. Now to this example. Again, an aryl palladium halide, carbopalladation. We have the opportunity to form a 7-membered ring, 1, 2, 3, 4, 5, 6, 7, That would be a cyclization in the sense of 7 endotrick process. However, a 6 exotrick process should be preferred. So, carbon-carbon bond formation from here to there, 1, 2, 3, 4, 5, 6. Beta hydride elimination is not possible because there is no beta hydride but a quaternary center. So the next carbo palladation would be performed, of course, at that olefinic double bond. Once again, a 6 exotrick process. Now there is no problem in performing a beta hydride elimination, since this CC bond can rotate and the palladium and the hydrogen can adopt a Zyn periplanar position. Under certain reaction conditions with the right ligands, this would be the final product under the reaction conditions that have been used in the publication, but the details are not important. Well, it was shown that since the hydropalladium iodide is still coordinated to the double bond, a re-addition could occur with the opposite regioselectivity. So hydrogen, then at that position, palladium here, again beta hydride elimination, and as the final product, then the spirocycle with the CC double bond in conjugation to the 3 electron pairs of the oxygen was obtained. Certainly thermodynamically more stable compared to the one with the exocyclic double bond, and the yield that has been reported is 60%. This example is somewhat tricky. One could imagine the first step after the oxidative addition of a palladium 0, a 6 endotrick cyclization. Maybe this is one of the competing reactions that one could prove when looking for the product mixture in detail. However, 68% yield of a product was isolated which clearly derives from a 5-exotrig cyclization. This is certainly an intermediate and certainly a free electron of a nitrogen will sometimes coordinate to the palladium, stabilize that structure. However, the palladium is sitting there and waiting for an opportunity for completing the catalytic cycle, and it has the opportunity to attack as an electrophile this CH bond. One can discuss what's the detail of this type of reaction. There seem to be some examples where a direct oxidative addition into a CH bond occurs. However, in this case you can also discuss it as some kind of electrophilic aromatic substitution intramolecularly with a palladium +2 as the electrophile. So, if you assume a pallada cycle as intermediate, then a reductive elimination will connect the carbon centers, CC bond formation from here to there. Leads us then to the final product, which has indeed been obtained. This one with a yield of 68%. Next example. Structures are getting more and more complex. So, now let us discuss which CC bond has been formed by the palladium catalyzed process. Usually it should be close to the double bond. But remember, we have already seen examples where the double bond can migrate. For instance, this case here. One could assume having some kind of benzylic halide here with no beta hydrogen forming the CC bond. While somewhat problematic, it could react here, but presumably then the connection would be from this position to that one. More an exotrig cyclization. Therefore, the alternative is this CC bond. So, and the structure we should start from should be this one. A tertiary amine with this substituent easy to be introduced just by nucleophilic substitution of the secondary amine with such a bromide. So, and then clearly again oxidative addition to the carbon, usually halide bond, then carbopalladation and beta hydride elimination to form the thermodynamically preferred donator-acceptor substituted olefin. Some more examples with a migrating double bond. Allylic alcohols. With this monobromo benzophenone. Reaction conditions: sodium acetate as a base, DMF, palladium acetate as a palladium-2 salt, which is reduced in situ, 90 degrees, 6 hours reaction time. Well, okay. Oxidative addition to the carbon bromide bond, carbopalladation at this double bond, then the palladium has the choice for the beta hydride elimination to this or to the other position. Let's draw this situation. So the palladium is sitting here. Beta hydride elimination to this position has the advantage that we get a conjugation to that benzene ring. However, in this direction, we have both conjugation to the OH group, we form an enol, and the conjugation to the other phenyl group. Actually, even if we don't have a phenyl group, just an hydrogen there, usually the elimination to an enol is preferred, which then, of course, soon tautomerizes to the ketone, giving this result. And indeed, this kind of reactions work very well. 92% yield is reported. And a second example, with a bromofluorinone, leads to the analogous product with 80% yield reported. This type of reaction also works with homoallylic alcohols. A 43% yield is reported for this case, while the yield in this case is not that good. However, I think the problem is not that we have a migration through that of a double bond through the chain that is a bit longer, since to my knowledge it has been even tried to perform these migrations on chains with up to 10 carbons, and it nevertheless works. The problem is, remember, we work in basic reaction conditions, and of course then aldol addition, aldol condensation at higher temperatures will be the competing processes. Therefore it's rather difficult to obtain the aldehyde as the product. First problem I would like to ask you to think about is, here we have a highly functionalized ring system, a quinoline ring system. What are appropriate starting materials for synthesizing this with a Heck type reaction? Again, palladium catalyst and base. And afterwards, please think about what will be the results of the following reactions. Iodoaniline plus a homoallylic alcohol. Reaction conditions in that case, again, palladium acetate, DMF. A sterically hindered amine, diisopropyl ethyl amine, called Hünix base. Well, 120 degrees, 2 days reaction time. Then diiodobenzene plus an excess 2.5 equivalents of the parent allylic alcohol. Very similar reaction conditions, 80 degrees, and also 2 days reaction time. And a final example. With an alpha-beta unsaturated carbonyl compound and the homoallylic alcohol. Again, similar reaction conditions. So please try to figure out what will be the products. In this case, which products would you anticipate? And here in this case, what is the appropriate starting material? So let's start with this example. What we have in the product, this side chain with a carbonyl group, and we have learned that a side chain with a carbonyl group we can introduce by Hack-type reactions with allylic or homoallylic alcohols, and therefore it is a good idea or an interesting idea to form this carbon-carbon bond. In this case, we have to start from a quinoline with an additional group X, which should be more reactive for the oxidative addition reaction with palladium 0 than the chloride. No problem if X is either bromide, iodide, or a triflate. What else do we need? Just this allylic alcohol. This reaction works quite nicely with an iodide as the substrate and an 85% yield was obtained of this product. Most of you noticed that these examples are always Hack-type reactions with allylic and homoallylic alcohols, then connected with some reactions which are, of course, classical carbonyl reactions you know from organic chemistry 2 lectures. So, here, carbopalladation at that double bond will introduce then the migration of that olefin until the enol is formed. The enol doesn't react with the aniline functionality, but after tautomerization we have a carbonyl group here, and then simple condensation to form an imine will occur. So let's count the centers. 1, 2, 3, 4, 5, 6, 7. Imine formation in this case then is a 7-membered ring. Well, then it's a benzoazepine. which was obtained with a 63% yield. The competing product with 21% yield was the one where the double bond didn't migrate but stayed in conjugation with the phenyl ring. In this case, the Heck reaction will take place twice. So, and remember, now we have the situation, elevated temperature, 80 degrees, two aldehyde functionalities, basic reaction conditions. They will, of course, not survive 2 days, but basic reaction conditions are suitable for aldol addition and aldol condensation, especially at the elevated temperatures. So, aldol condensation, let's see how many positions do we have. 1, 2, 3, 4, 5, 6, 7. A 7-membered ring will be formed. (81% yield). In this case, a homoallylic alcohol, nevertheless, migration of a double bond will give an enol. So, the enol could tautomerize to the aldehyde, and have a look at that setup here. It's well suited for some kind of Robinson annulation. Maybe the enol doesn't tautomerize, but directly will undergo a Michael addition reaction. Then we have that carbonyl group, and here an aldol condensation can take place. Forming this ring system. 72% yield and cis-trans selectivity of 1 to 4 was the result of the analysis. Finally, for today, let's have a look for an interesting publication by Ravel, published in Journal of Organic Chemistry in 1993 on page 5583, and it had the title "An Unexpected Heck Reaction." Ravel from the Ohio State University became rather famous for his syntheses of strychnine alkaloids, and also this publication with the unexpected Heck reaction was in the context of these studies for the synthesis of strychnine alkaloids. a substrate that he tested already rather complicated, so you have to do a multi-step synthesis to get to the opportunity to let this system react. A vinyl iodide, an olefinic functionality, hydrogen here, and well, he was using the Jeffery conditions I already mentioned before. That was 5% palladium acetate, tetra-N butyl ammonium chloride, potassium carbonate as the base, DMF, and 60 degrees as the reaction temperature. What he obtained for the case that the substituent R is just a hydrogen, was this structure. Sorry. With a 79% yield. So, what happened? Reduction in situ to palladium 0, oxidative addition reaction, then a carbopalladation of this CC bond. So, this is a ring closure reaction. According to Baldwin, it should be a 6-axotric process. Let's count the positions. 1, 2, 3, 4, 5, 6. Okay, 6-axotric. Okay, so that means after CC bond formation, he had the palladium sitting here on the same side as those substituent, and then just a beta hydride elimination to the enamine, and afterwards a tautomerization from enamine to imine occurred, and this explains this result. Same reaction conditions, but as the substituent R, not the simple hydrogen, but a carbamate. The result was even better, 84% yield, and the Ravel group needed some time to figure out what's the structure of a product. This one. Isolated with 84% yield. So remember, this was a 6-axo trig cyclization. So, and on the first glimpse we should assume, well, the double bond is there, CC bond formation took place from this position to that one. Let's count 1, 2, 3, 4, 5, 6, 7. Unusual, a 7 endo trig. But additionally, question mark. 7 endo trig, this is rather strange. So we analyzed it and figured out a modified mechanism which takes into account that the carbamate group must have an influence, of course. Okay. So 7 endo trig process would be highly unusual. Why not assuming that in the first step the same thing happens as in the first example? So that means again a 6-axo trig cyclization. And the influence of that carbamate group should have something to do with the fact that this is a suitable nucleophilic ligand for the palladium, and the palladium is complexated and somewhat stabilized. I'm going to try some kind of perspective drawing. A chair conformation for this 6-membered cyclohexane moiety. Okay. Now to the palladium. At an equatorial position. And a closer look to a model of this structure reveals that it is somewhat fixed in a conformation where the dihedral angle between that palladium and that hydrogen is about 55 degrees. For the beta hydride elimination to occur, the system would need to adopt a dihedral angle close to 0 degrees. This is somewhat hindered by that complexation. Somewhat strange or surprising is that we have an alternative reaction, a carbopalladation, now from that center to that olefin here. So the carbopalladation, in a sense of a 3-exotric cyclization, is indeed feasible. We have seen that before in one of those initial examples forming a 3-membered ring. I hope you remember. So, that means a 3-exotric cyclization connects this carbon with that one, and the palladium will sit then at this position. 3-exotric cyclization. Will form a 3-membered ring here, so the question is, how could we now get from this situation to the final product? Well, we need the double bond there, so that means the palladium has to change the position from here to there for the beta hydride elimination to occur. That means, and also the CC bond here has to be broken. You have to break that CC bond. Yeah, well, this is possible because a retrocarbopalladation would just break the CC bond and transfer the palladium to this position. Okay? So, and then, well, we are just in the situation we need for the final beta hydride elimination. So, and fascinating certainly is that it explains the final stereochemistry at that olefin. So, for the retrocarbopalladation, that means the better carbo elimination to occur, this has to rotate. So, that carbopalladation step gives us this stereochemistry. This CC bond is in front, that one is behind, the palladium is in front, but the palladium for the beta carbo elimination has to adopt again a syn-periplanar position of the C palladium and that CC bond. Means this has to rotate and will bring the methyl group to this position. Okay? And then that beta hydride elimination here finally will lead us to this product. And have a look at the situation. The stereochemistry at that double bond has changed to the opposite just because of the necessity of that CC bond to rotate with the palladium to transfer it in a suitable position for the beta carbo elimination. So, this mechanism then nicely proves the stereochemical outcome of the reaction, and this is an interesting proof, I think, and a fascinating palladium catalyzed process we can learn a lot from. Thank you for listening. See you tomorrow.